Yep. So good afternoon, everybody. Thanks for coming for the Learning Lab 13. So today I'm going to be continuing talking about clusterings model that we started two weeks ago in the Learning Lab 2. Let me just mute my video. And it's going to be presented by me, by Daniel Tread and David Emery. So just an introduction about us. I'm Marcelo Guarido. I'm a data scientist, and I'm the head of the Cruise Data Science Initiative. So I'd like, Daniel, could you present yourself?
Yeah, I'm associate professor here in the Department of Geoscience, and I teach a course in machine learning.
Thank you. Dave?
And I'm David Emery. I'm newly retired after 34 years in industry and been working with the cruise and will be an incoming PhD student with Daniel in the fall.
That's nice. So just an introduction, what's the Cruise Data Science Initiative? It's a subgroup of the Cruise Consortium at the University of Calgary. And this Cruise Data Science Initiative is going to be focusing on data science projects that are related to machine learning, data analysis, data engineering, and all this kind of stuff. And we are mainly focused on geoscience projects, but we are open for other type of projects like renewable energy projects. And we do projects both in the academic and industry guided projects. We also provide some training in programming languages like R, Python, and MATLAB that can be very introductory courses, like how just to do the programming, as well as for more applications in machine learning, and also to create apps using Shine libraries and things like that. And also we provide the learning labs that those are the free webinars that we present every 2 weeks. And you can access all the information from the old labs in the Cruise website. If you go to thecruise.org, you can go to the research links tab and data science. You're going to see all the old labs that we presented in the past, and they are all free for you to watch the video and download the files, all the programming that you used for that specific lab. Okay, so today we are going to be talking about a small paper overview. That's going to be the same paper that we did 2 weeks ago, just to continue this clustering applied to the energy sector. We're going to talking about a little bit of clustering. I'm going to explain again the different types of clustering, that they can be centroid-based, distribution-based, or density-based. I'm going to talk about the Scikit-Learn package that you're going to be using today for all the coding. And then we go decoding for different models in Python. So last week, we tried 4 different algorithms or 4 different methods. And today, you're going to try other 4 different ones. So just a fast overview for what we presented 2 weeks ago. We are basing these clustering presentations in this paper, Machine Learning Assisted Velocity Outpicking by Ken Smith, 2017, where he used k-means for unsupervised learning to do a seismic velocity outpicking. So the idea was that he created the semblance for the velocity and created using a guiding velocity. That's this yellow line in here. Created a guided peak in here that could be all these blue points that would pick just maximum points at every position in here. And then he did a clustering over these points in here, these data points, to create the centroid of each one of the clusters. And then he considered that each one of these centroid is actually the velocity peaked. So those are some of these results. When you do just brute stack, is brute velocities. And here we are the semblance outpicked, the AVO outpicked, and this is the machine learning approach. So he claims by pointing at these positions with these red arrows that you have a more clear continuous layers and higher density brute stack when you use the machine learning peaked velocity. So this is the resource that's going to be available. If you download the presentation, you can go to the paper and download the paper. And just talking about the clustering models, like we did the last time, the Learning Lab 12, we have the centroid-based models that basically are going to have some linear separation between the clusters. We have the distributed based ones, which considers the distribution of each one of those clusters. So this is going to be the Gaussian mixture that you're going to be presenting today. And the density based, where the clusters are going to be picked based on the density of the points. So if there is a high density position, so those points are going to be entering a cluster. And points that are outside this high density, usually they are marked as -1 or no cluster. Last week, not last week, in the Learning Lab 12, the last week, we presented the k-means, the affinity propagation, the mean shift, and the agglomerative clustering. And what you're going to be showing today are the dB scan, that's also a density-based algorithm, the optics, that it's a generalization of the dB scan, the spectral clustering, also another density-based model, but it's also based on graph. So that's a very nice way to do the clustering. And we're going to end talking about the Gaussian mixtures. That's a distributed based one. That's a very interested, and I would say that's kind of my favorite to try doing clustering in projects. So let's go for the code. I know the presentation was short, but I want to show something very interesting that we can do in the VS Code. So like we did last week, we showed Ipython notebook or the Jupyter notebook that we opened in the VS Code. That's an application where you can run different languages. I also run HTML, R. You can even run MATLAB in here. And what we did last week, we created a Jupyter notebook, this Lab 12. We just deleted this one because I want to show something very nice. So we have this Lab 12 Ipython notebook, and here we have basically what is a Jupyter notebook. We have the cells that you can run and visualize here like we were in the web browser, in the Jupyter notebook. What I'm going to be showing today in the Learning Lab 13, the clustering, second part of the clustering, is that you are going to be running in a .py file. It's not a Jupyter notebook anymore. I just want to show what is the advantage of this that works very nice on the VS Code. You can create actually in this macro type of coding. You can also create cells if you use the pound and percentage, and you can create markdown cells as well. Coding cells. Coding cells is going to have nothing after this, the initializer of the cell. So the initializer of the cell is this pound sign, percentage. And you can create all the markdown like you do in here, the same markdown. But when you run this cell, that you can run this cell by clicking run cell or doing a shift enter, it's actually gonna show here on the right in an interactive window. So that's the interactive number 1. And it's gonna show exactly the same Jupyter Lab or Jupyter Notebook that you had before. So people are gonna say, so if it's gonna visualize the same, what is the advantage to use this way? Well, I like to use this way because you can run several times the same cell. For example, we run 3 times the same cell, and it's gonna show every time that I'm running. So if you're running a code section and you do a plot and then you do some changes in here in the parameters, you're gonna see the next plot and the previous one is gonna, be saved in here. So you're gonna see everything as it was before running. Another advantage that I like, this is more for presentation in the coding, For the VS Code, you can also select the code that you want to run. For example, I want to run all this code. So you select and also do Shift Enter. What it's going to do is going to run in a terminal down here. And the advantage to do that is that you can open part by part of the code and run just parts of the code to see what's happening. For example, what is this load digit? So I'm just going to just select this part and see what is the output. So the output, it's a tuple of two NumPy arrays, basically. And you can see what is data that was created in here. Just select the data and run. I can see that's a NumPy array. Labels in the run, I can see also the NumPy array. Another advantage is that I can keep moving the code in here. For example, I just plotted for the DB scan, and then I want to compare with the last one, that's going to be the Gaussian mixtures. I can see both on the side here, or I can simply run each one of them. I'm just going to run very fast and show. So this is going to be the clusters for the original data. I can save the picture in another tab, and then I can compare. So it doesn't matter what I do in the interactive window. This figure is going to be saved here. So every time that I have a final figure that I want to compare the clustering, I'm just going to be saving here, and then I can compare. So if I do again, I'm going to have a second one. So imagine that I have two different figures. I can keep comparing them by just doing that. And from here, you can save the PNG file. So it's going to be quite simple. I want to cancel. And you can even delete this image from this visualization by clicking here. So that's how we're going to be coding today. We're going to be using this one. So I'm just going to restart everything. Oh, sorry. Another thing that's I like that's quite interesting. I'm just going to close also the terminal. Is that you can go in here in this button, show variables that you have in your Jupyter kernel. If you click here, those are all the variables that you created in here. For example, the data, the labels. And you can even visualize them. You can click here, and it's going to open the data viewer. What is this data? So this is a NumPy array. So we have the index, and the column names are just going to be also indexes for the column name, basically. And you can visualize your tables in here. We even have the reduced data. That's going to be just a two-column version of the data. So that's why I like to work in this type of environment. Now I'm just going to reset here the kernel. Let's just start from the beginning. I just restarted the kernel. I'm just going to clean all the outputs, remove all cells. Just remove this one. And now let's start from the scratch. So now I'm going to run this first cell that's marked down. And that's what we're going to be presenting today. We're going to be continuing what you're presenting the last learning lab, different algorithms that you have for clustering. And today I'm going to be talking about DB scan, the optics, the spectral clustering, and Gaussian mixtures. The data set that you're going to be using, you're not going to be using any energy related data set. You're going to be using something from the Scikit-Learn data sets, actually the load digits data set from the Scikit-Learn. So if you click here, you're going to see it's going to send you to the browser and the different types of data that you have in the Scikit-Learn. Those are kind of the toy data sets that you can train and see how each one of those models work. What you're going to be using today is these load digits. If you click here, it's going to explain everything about the data set. Basically, those are digits, handwriting digits from 0 to 9 that are originally 8 by 8 images, but it was dimensionality. It changed the dimension. Instead of you're going to use 8 by 8 images, it got each pixel and saved in one column. So we end up to have a data set that has 64 columns, that each column represents 1 pixel, and have integers that go from 0 to 16. That's one of the representation for grayscale. And we have a total of 17, almost 1800 figures or data points. That's the data that you're going to be using. That is the description. The metrics that you're going to be working today to evaluate our clustering are going to be the homogeneity score and the completeness score. If you click the link in both situations, it's going to open how it works in the Scikit-Learn. So that is all the documentation. You can go to the user guide and it's going to explain what each one is doing, all the equations. And the homogeneity, it's going to give a number that represents each clusters contain only members of a single class. So it's going to count inside a cluster that you know the answer, only members of a single class. And for the completeness, so all members of a given class are assigned to the same cluster. So basically, it's just counting how many correct answers you have inside a cluster, and here how many correct clusters you have inside a class. So that's how they are measuring, and both assumes values from 0 to 1, where one is the best scenario and 0 you made all wrong. And now for the first clustering, we're going to be using the dbScan. So dbScan is called density-based spatial clustering of applications with noise. Is a density-based algorithm that scans the clusters by looking at their neighbors. So it's going to start at one point, like this GIF is showing, and there are a few parameters that you have to change. The minimum number of points that you want inside this distance between the central point, and what is the radius of this circle in here. So if it satisfies the condition, if I want a minimum of 3 points and you have minimum 3 points in here, that satisfies each one of the circles, is going to keep scanning all the points and saving in the same cluster number until it's not satisfied. So it's going to try another set of points with a new cluster number that satisfies the condition that you created initially, and going to do the same until you have no more clusters. And all the points that doesn't satisfy those conditions are going to be classified as -1. That means they are not in a cluster. The advantage of this kind of clustering is that you don't need to set initially the number of clusters that you want to have in this data set. It's going to find for you automatically. So here, now let's start the coding. Here I'm going to be importing some of the important libraries, NumPy, because I'm going to be using NumPy arrays from the datasets, Scikit-Learn.datasets module. You're going to be loading the load digits from the cluster in this one, the dbScan. From the Scikit-Learn decomposition, the PCA. We are not going to explain what is PCA today, but this is also unsupervised learning, but for dimensionality reduction, where we're going to do a 2D representation of our data that has 64 dimensions. So just for plotting. So I'm not going to explain. We're just going to say that we are just finding a representation of our data set in a 2D space. And also we're going to be loading the metrics, the homogeneity score and the completeness score, as well the matplotlib. And here I'm just setting the style to be seaborn. So sometimes I select this style because it's going to be the same. It doesn't matter of the theme that you have here in your VS Code. If you go to change the theme, it's just going to show you. So that's how you're going to change the theme. We have different colors that you can have. My favorite that I like to use is a dark. I don't know if you guys like dark themes while coding. Usually I like. I see better the colors in the coding, and I see everything better when I'm coding and makes my eyes less tired. And because of that, the PLT style is going to be Seaborn. So let me just run in here and show again the plot. So it's going to be the same style. Doesn't matter if it's a dark or a not dark layout. We do that because the VS Code is going to try to optimize your layout depending of the theme that you're using. If I just comment this line, if I restart my kernel, and let's just do that and run again the plot. So that's what it's gonna try to do when we have the dark theme. Now, if you go to the light theme again, probably if I try to run again, it's gonna still be dark because I didn't reset my kernel. So if I reset my kernel and do again the plots, now it did a light one. So when I keep this one uncommented, I see that I wanted to use this style Seaborn. If I run, so it's gonna be this style, doesn't matter if you have a dark or a light theme. So if you go back to the dark theme, let's just reset the kernel. So now we have the same type of plot. So I like this. So do you guys prefer for this presentation today, the light or the dark theme to present today? Do you have any preference?
Dark.
Dark, okay. So let's go for the dark then. So I'm gonna just reset everything. And if I want to run all the cells above that I have in this cell here, for example, I just click here, run above. So I'm just gonna run all the markdowns one that I had above, and now I can continue. So I'm just gonna run this part. And again, so here we are loading the digits. So here we are loading the data set. And we just set one of the hyperparameters is that to return the X and Y, means that you're going to return one matrix that has 64 columns and an array that is just a 1D array that are going to be the labels or the true labels of each one of the handwriting digits. And the first one, the X, that's going to be the 64 size data. It's going to be in data, and the labels are going to be here. Also here, we are just gonna get some information from this data set that you're creating. We wanna see the shape. So we wanna see the number of digits, basically. That's gonna be the NumPy, the unique labels dot size, and also the shape, the number of samples and the number of features. So it's plotted here on the side. So the number of digits, we have 10 digits, 0 to 9. Number of samples, that means the number of rows in our data set is going to be almost 1800, and the number of columns, 64.
Oh, Marcelo, can I just interrupt you a second? I'm a bit confused. We start by talking about this velocity semblance paper, which I just downloaded. And then we immediately move to smiley face here, but I don't see what smiley face has to do with that velocity semblance.
Oh, no, this is just a representation. This is just explanation how the DB scan works.
Right, but in their paper, they don't even say which techniques they're using. So I really, they just say we use a machine learning algorithm for clustering, and they don't even mention whether they're using DB scan or any of the ones you're showing us. So
they actually used the k-means.
They were using k-means?
Yeah.
So wouldn't it be possible, maybe Dave Emery Dave, do you have the ability to produce a semblance plot? Maybe we could try it on a semblance plot?
Not quite yet. Marcelo and I have been doing, of course, looking at the different clustering on some well log data.
Okay.
But that's kind of future work. Right now, we're just trying to demonstrate through the different the 4 clustering methods.
But isn't the whole idea here to look at applications to the energy industry? And these are just toy examples from Scikit-Learn, right?
Yeah, for today, we're just going
Just
to
to
be
learn the algorithms, I guess. Eh?
yeah. Today, we're just going to be learning how the algorithms work, and
Right.
the next lab, actually, we're going to have the guest that's going to be Ninoska, and she's going to also show the semblance application.
And is she? Oh, she's going to actually use a semblance plot. Okay.
Yeah. So today, these
Okay.
first
So
two
you're just
labs.
explaining the methods.
Yeah, I'm just explaining what are the different algorithms that you can use, and then Ninoska is going to give
yeah,
out to us.
that is what I was going to clarify, Brian. Yeah, so we have a project with Ninoska where we create synthetic data with seismic units with different models. And then we try all these different, we create the semblance again with seismic units. And then we try different models, like we did k-means. We actually did the Gaussian mixture is the one that works the best. So yeah, I guess we will. I didn't know that Ninoska was going to present this next time, but I was. Yeah, we will discuss that after. If you want, I can show you some of those too.
Sounds good. Okay, so I'll look forward to the next one too. Yeah.
Yeah. So yeah, today is just, let's say that's an introductory class, and then the application is going to be next learning lab, the learning lab 14. Ninoska might be laughing now that she's going to present in the next one. But... So here,
yeah, if you know at the end, Marcelo, I can share 5 minutes or less. I can show a few examples so it doesn't get that disconnected.
Okay, perfect. So just continuing. So now we're going to give a 2D representation of the data set. If you remember, if we look here in the data that we got, we have 64 columns. But to plot here, to see our clusters, we cannot plot these 64 columns. So what you're going to be doing, we are going to be doing a reduced data set. We're going to be using a PCA, and we're going to reduce to 2 components. That means that we're going to have 2 variables only. And that's the way we run the PCA, and then we do the transformation of the data set. So here, I'm going to be plotting, and this is the data set, the distribution of this visualization, the PCA, the 2 PCAs, and each one of these, the labels, where each one of these colors is represented to a handwriting. So the 0 is going to be black, the 9 is going to be gray, and all those colors in between. So again, I'm just going to save here in the plots, right ahead. So now we know the original data set, the original label. And now we're going to run our model, the DB scan. So initially I included this time here, just because you are measuring how long does it take to run. You're going to see that, for example, the spectral clustering takes longer to run than any other method in here. I'm just getting the name of the model. That's going to be DB scan, just for plotting, just to print in the results. And this is how you're going to be using the function DB scan. So if you go back to here, we have the DB scan. If you click in this link, so it's going to open for you the documentation in the Scikit-Learn, and all the important features, or sorry, all the hyperparameters that you can change here. We are going to be focusing on the EPS, that basically is the radius or the size of the circle that you want to create to consider all the closest points as the same cluster, and the minimum number of samples inside the circles that you need to have to be considered a cluster. So if you have only 4 points inside this circle or inside this area, so it's not going to consider a cluster. So it's going to probably classify as that -1. And also another thing that I'm setting here, the number of jobs, say that I'm setting to -1, because I'm going to be running on all my CPUs, so to run faster. Here I set the default parameters for the EPS, that's 0.5, and the minimal samples to 5. And you can see here that I already set the optimal for this situation that I could find. But let's see first how it's going to run. So I'm going to call the DB scan, set the parameters, and I'm going to fit the data set. And I'm going to save in this object named dbScan. That's going to be the model with the trained weights. Then we're gonna compute the metrics. So first the homogeneity, and second the completeness. So from the dbScan object, we can get the labels that were predicted. If you do dot labels underscore, and then I'm gonna save our results in a string format just to print. And they're going to be plotting in here the number of clusters that it's determined, because you don't set the number of clusters that you had initially. And also you're going to print what are those clusters that it found. And in the end, you're just going to show the same plot with all the clusters in that 2D plot like this one. So if I run this cell, it's going to run all at once. And that's what we have using the default parameters. We had a model for the dbScan where the homogeneity is 0 and the completeness is 1. That means that's why we are using two different metrics, because the completeness, if you set all the points as one cluster, this metric is going to be 1, but the homogeneity is going to be 0. When you set all the points, each point as one cluster, the homogeneity is going to be 1, and the completeness is going to be a very small number, 0.2 or something like that. So what you want to get is one combination of hyperparameters that gets a balanced metric for both of the metric. Here we have the number of clusters. We actually have no clusters determined, because when you see here in the plot, it said that all the points does not belong to a cluster, is the -1. And the unique labels are -1, and how long it took to run in this computer. So one way to work with that, we have an idea how the clusters are, is to start looking in this point. So just following some logic, if it's setting that all the points are not clusters, that means that you couldn't get these conditions, met this condition that for this distance, we cannot get 5 points to be neighbors. So one first try that you could do is just starting increase the radius. For example, if you do 2 for the EPS, nothing changed yet, so probably we have to go even larger. So we can try 10, not yet. And that's how we hyperparameter this. So I tried now 20, and now we have something. Now it starts to find clusters in here. The only point that it found 24 clusters, or sorry, 25 clusters, plus the -1, all the points that do not belong to a cluster. One way to work with that, to separate the clusters now, is to change this condition, the minimum number of points to be a cluster. So if we increase to 10, now we reduced the number of clusters to 14, for example, and things start to get a little better looking. And if you do those values that I found here, that was 24 for distance, and the minimum number of samples, 20, that was the best that I could get. We actually got those metrics. Those are pretty good metrics for this one. 9 clusters, considering the 0 to 8, plus the -1. But if we actually compare with the plot that we had initially for the original ones, this -1 is actually very close to the cluster number 9 that in here is in black and in here is in gray. And also a little bit mixture of the red one, that's the 8. But all the other clusters, for example, the number 0, sorry, the number, yes, the number 0, it's actually being found in here very well for the DB scan. This one, that's the 6, got very well defined in here as the cluster number 2, and so on. So actually, this worked pretty well for these data sets, but
So
we still cannot.
Sorry, can I just ask another question? Is EPS the radius? I missed that definition.
Yeah, it's the radius.
Okay, so you need the radius and the minimum number of points for DB scan to work, right?
Yeah.
So have you tried different, how small a radius have you tried?
Oh, I started with the default, that's 0.5.
Okay.
And then everything is set not to be a cluster.
Oh, I see. Oh, okay, that's what that was showing. I was confused about that plot. Yeah. Okay.
Yeah.
Yeah, but Marcelo, that would be a bit different if you had normalized each of these to 0 to -1 and +1, right? Because you're using the full here axes.
Mm.
Yeah, I'm using from 0 to 16. Those are the numbers that the data set assumes. And those numbers are going to be dependent if you're going to normalize it or not. So if you normalize before, those EPS are going to be different, definitely.
So did you try value? So you started with a very low number. Now you're up to 24. I must have missed. Did you try some other values in there?
Yeah, I tried, for example, 10.
Okay.
We still got just 1.
Okay. Yeah.
I tried 15.
Oh, there we go. Okay. Oh, okay. Okay.
Then we have 1, but very small, and so on.
Ah, now I see. Okay. I must have missed that point at the beginning. Good.
That's okay. And here, that's the best that I could get. I was trying yesterday different ones, and that's the best that I could get. And by showing the plot, this is the original labels, and those are the results from the DB scan. So the colors, they're gonna mesh differently because the numbers of the clusters, they're gonna be kind of random generated, which one is the first or the last one. But the position of the clusters, we see that it's working pretty well. One thing that I couldn't separate was those 2 clusters, that is the number 3 and the number 9. So it could not separate properly, the 3 and the 9. But it did a pretty good job. So for that, we went for the next clustering that's named optics. That's basically an expansion of the DB scan, so a generalization. The main difference is the EPS parameter. That's now it's a range of numbers. So if you click here, we can see the explanation, the documentation. So instead of to have one single EPS, we define what is the maximum EPS or the maximum distance that can be satisfied. And the default is going to be the infinite, the NumPy infinite. You can set different ones to reduce the run, and that's what you're going to be working with. So you're going to be also working with the minimum number of samples and the max EPS. So, and that is this actually xi parameter. So let me just return in here. This xi parameter, when you're using a max EPS, so it's just the minimum steepness that gonna contribute to the cluster boundary. So that helps a little bit as well. So you can see that I already found which one of the best that I could get. So let's start with the default parameters. So here the same, we are loading the optics. So all the hyperparameters that can change, the number of jobs we are fitting or training in our data set with 64 columns, calculating all the scores and plotting here. And from now on, we're going to start to compare with the previous one. And also doing the plot. So if you run this now with the default parameters, you're going to see that's going to take a while to run because it's making a scan on different EPS values. And that's what we could get initially with the default parameters. We could get 31 clusters plus the -1. And if you see here in the plot that most of those clusters, they are quite small. They just have a few amount of points. So what I started to play with first is to define this max EPS, and based on dbScan, I tried similar values that we had there. So I tried, for example, 20. So it's gonna run faster. It's not gonna run to the infinity anymore. Actually didn't improve much. We have even more clusters than before. So then I start to work with the minimum number of samples. So I tried initially 20 as well and see how things change. Now we have just a few clusters. Even the metric for the homogeneity got worse, even though the completeness got better. Remember, everything that's set as one cluster is going to be one here. And I even start to change what these values does. So I just changed it in here to 0.1, for example. For this plot, it didn't change much, but when I did these 10, so basically I got to these values by trial and error. I started to try different numbers. So I got one number that made more sense now. So we have 13 clusters plus the -1. And the metric got better and it started to look like our original figure as well. And the final value that I got here, it was 22.4. Don't ask how I got that. So when I run with those metrics, I could get 10 clusters plus the -1. Those are the metrics that I could get. So now they are quite closer to the dbScan. And that's the final plot that I got. So, and also if we compare here to the dbScan, those are quite similar ones. The main difference now that we see is that we're supposed in the original one to have 3 clusters in here, the 3, 9, and 5. For the dbScan, couldn't separate it. It's 3 and 9, and now here could separate it. That's 3, 9, and 5. So those are the main difference. So these optics, I couldn't work it to have a better metric to work for this specific data set. So I tried other different clustering methods. So the next one that we tried was the spectral clustering. This is a different method for clustering. So it's a graph-based algorithm where it's gonna create a graph and then you're gonna create, using those graphs, affinity matrix, where you're gonna calculate the aging values and aging vectors. And from the aging vectors, you're gonna do a clustering over the aging vectors. So the aging values is gonna determine how many clusters you have. And from the aging vectors, you're gonna get the clusters. So you're gonna run, for example, k-means over the components of the aging vectors, not the aging values. I just typed it wrong in here. So should be aging vector.
Do you know what kind of norm you're using here? Is it a Euclidean norm or is it a?
I think that's the Euclidean in this one.
That's the default, or is are there other types?
There are. If you go, for example, for the optics, it's gonna use in the Minkowski.
Okay.
And the dbScan is gonna use the Euclidean. And basically, all the defaults in general are gonna be Euclidean.
Mm.
For the spectral, I had to set the parameters before, because if you use just the default, it's actually not gonna run. It's gonna enter in an infinite loop somehow. So there are different solvers for the eigenvalues. Let's just go here and click in the documentation for the spectral clustering. So things that you have to determine before is the number of clusters. So you have to know how many clusters you want. So we determine as to be 10. You need to have the eigenvalue decomposition strategy. So the eigenvalue solver. For that, they have these options. And for the AMG, actually require for you to install this library, PyAMG. So, but that's the one that worked better. It's faster and better for sparser problems. Those number of components is the number of eigenvectors for the spectral embedding. We have to set the random state, the n init, then how many numbers of times you want to start the k-means algorithm when you're doing the clustering of the eigenvectors, and it's gonna get the best of them. So the default is gonna try 10 times with 10 different random starters. And how to do the affinity as well. We have the nearest neighbors, RBF, and you have all those options. So what I could get better for these ones is for the agent solver to be the AMG. For the any needs, I kept the default 10. So I'm gonna try 10 times. And for the affinity, I tried the nearest neighbors. So just remember, this affinity, it's how to construct the affinity matrix. So it's just do that by constructing the affinity matrix by computing a graph of the nearest neighbors. If you select the RBF, that's the default. So it uses a radius basis functions, the RBF kernel. It quite worked well for nearest neighbors. If I try the RBF, I could just try here what's going to happen. For the spectral clustering, and I set the random state to be 0. So every time you run, you're going to get the same result. And everybody that tried to run at home, all the scores, all the plots, and everything. So when you run, we had this warning that says the graph is not fully connected. So the spectral bidding may not work as expected. If I just keep like that, it's actually not gonna end to work, to run. So I have to stop, I have to queue this running. And that's why I used the nearest neighbors selection for the affinity. When I run here, it actually ran. And I could get actually the best metric so far. So we got the 10 clusters, and this is the plot. So I tried different combinations, but every time it just didn't run. So those are the combinations that could run with no infinite loop. And this is the plot. So we can compare now with the others. If we compare to the original one, we are still not be able to separate what is the number 3 and 9 properly. But all the other clusters, they seem to be working quite well, I could say. So for now, I'd say that that's the one that worked better so far. If you keep comparing. If you compare to the DB scan, you can see the difference that we have. And with the optics as well. But you're not separating yet the number 3 and 9. So that's why I'm going to the last one that you're going to be presenting today. Is that the Gaussian mixture. So that's basically my favorite one to run today. So I forgot to put a space here. So the Gaussian mixtures model. So it's a probabilistic model that works quite interesting. You're going to start with considering how many distributions you're going to have, and each one of those distributions are going to be considering your cluster. You're going to say how many distributions I want to find in my data set, And they're going to start with random parameters of this distribution. The random parameters are going to be the mean and the covariance matrix, or the variance if you just have one dimension. So what you're going to do, you're going to calculate the probability for each one of those points to be part of this distribution. For those, for example, these two distributions that had these random starters. After you assign, using these probabilities, the points for each one of those distributions, you're gonna recalculate the parameters of your distribution. So you're gonna recalculate the mean and the covariance matrix, and then you're gonna be keep moving the distribution for the high density position of the data. So basically it's a combination of the distribution plus density-based cluster. So that works pretty well. And if you want to learn more, you can follow those links in here.
Can I just say something here? Because I compared k-means and Gaussian mixture the week I did the lab, and it turns out that Gaussian mixture modeling and k-means are identical if you change the criteria from Euclidean to statistical in k-means. One's called the hard approach, and the other's called the soft approach. But they give, I've done tests, and they give virtually identical results as long as you put in the covariance matrices. But unfortunately, I don't think Scikit-Learn allows you to use statistical distance in k-means. Is that correct?
I think you don't. You have to check. I don't believe you can use a statistical distance in k-means, but we can check later. If you go here,
I think I looked and I couldn't, because I implemented it and came in Scikit-Learn as well.
So if you go to the k-means, the type of a distance that you can get, you can have a pre-computed distance, actually.
But if you look at the type of distance, I think it's only
I'm looking
Euclidean.
here. Apparently, you don't have the option to choose, say,
which is something a lot of people don't realize, that they're virtually identical. It's just different style of how they compute the do the updates.
Okay. Yeah, this one using the Gaussian mixture uses this expectation maximization.
Right.
That's where you keep updating the values of the mean and the covariance matrix.
Yeah, so that's the soft approach. The hard approach in k-means is they keep reassigning the points each time, right?
Oh, okay. Yeah. So basically that's how it's working. So here is the same way. Sorry, we open here the Gaussian mixtures. So there are a bunch of parameters that can change the number of clusters. So we're going to be setting to be 10 for us. Oh, sorry, I opened the wrong. Did I? Oh, it's the wrong link. So I apologize for that. So let me just get here Gaussian mixture. So I'll have to fix this. So here, this is the Gaussian mixture. So let me just change here quite fast. Here should be a Gaussian mixture. Then if I just change here now, this in this markdown, if I run, now I click here, now it's gonna open the correct one. So there are a bunch of things that can change, a bunch of hyperparameters. The number of components basically is the number of clusters that we have. And even to call the function or to import the function is not in the clustering module, it's in the mixture module in the Scikit-Learn. And to run, it's also a little different. Also, we have to change the covariance type. We have the options of full, tiled, diagonal, and spherical. The full, that it's going to create general covariance matrix for each component. The tide means that all components share the same general covariance matrix. The diagonal, each component has just the diagonal covariance matrix, and the spherical means that you just have a single variance. A few things that are going to be changed as well is just the covariance type, that the default is set to full, and the max number of iterations, that's 10. We're just going to be setting the random state to 0, and the number of components, that the number of clusters is 10. So basically, we are running here with the default parameters, and you can compare with the other plots. With the default parameters, we actually could get a very nice predictions already. So we got pretty much good metrics in here. We still having the problem to separate these two clusters. That should be the number 9 and 3, or 3 and 9. But what I did that worked pretty nice when I changed the covariance type to tied. So they have they share the same covariance matrix. I actually could start to get the separation. Even the metrics start to work better. So when you compare with our final one, the original, with this Gaussian mixture, we are actually getting almost perfect clusters in here. So those are well separated. This area is going to be a little harder to see because you have a lot of points, one above the other. All the clusterings, they are mixture in here. But in general, they'll work pretty fine. So you can see better separation between the clusters in here, with a few points going wrong. For example, apparently this one is wrong in here. This one should be a black. From this one, that's the number 0. Here should be a 0 at this position. But here it's classifying as these 6. That's actually a 6. Yeah. So the 0 is being classified as 6. So we can play more with different parameters, but those are the ones that I could get the better metrics. And in my opinion, worked even better besides of those metrics that we have in here. I think the Gaussian did a better job than the spectral clustering, mostly because of the separation of the clusters in here.
So your feeling is Gaussian mixtures does the best job, wouldn't you say?
Yeah, visually
Of all of
speaking.
them?
Yeah, because you have some confusion happening in here that might damaging the metric, but it's very hard to trust 100% those metrics for clustering. So you still need to go a little bit with your guts, or even use more metrics for clustering. I just selected 2. Probably I should have selected more. But I really believe that the Gaussian mixture is doing the best job in here.
Yeah, that's what I find too. I mean,
Marcelo, I had a question. Sorry, Brian. The k-mean, Gaussian mixture, etc. They don't have the -1, so the outliers, which the earlier in dbScan and others also has an extra class that says it can't classify that.
Yeah, that happens because it's gonna find the number of clusters for you. Here in the spectral clustering and in the Gaussian mixtures, you set how many clusters you want. So it's gonna force all the points to be part of a cluster.
Yeah, that's a good point. You don't know in advance what the optimum number of clusters is.
I'm also though thinking in the example from the paper where we're trying to get semblance center points, we do have a lot of noise. So having a cluster method that has non-assigned values would basically be saying that's just noise, don't use it. The Gaussian mean and the K clustering is going to attempt to classify every data point.
So one thing you have to do there, Dave, is always a thresholding, right? So semblance has a point everywhere, but obviously not everywhere is a point that you want to pick. So one of the things we have to do is apply a thresholding, and then another thing is selecting areas like a velocity trend where you want to keep your picks inside. So that basically take care of that problem.
Yeah. And here, for example, if you think in a DB scan and how it run in that smile plot, you can see that you have actually different densities in here. This area has a higher density than this area. So I don't know if it's gonna find automatically these 3 clusters in this area here. Probably can find 1 or 2. This one probably is gonna find another one. This one is gonna be a no cluster, I would say. It's gonna find another one here and probably another one here. The only problem is that we don't have a center of the clusters. We would have to calculate with the DB scan, knowing the clusters, and then you can manually just calculate the center by a Euclidean distance or the way that you want to do, or just by average them.
But you know, the real power of these methods is when you go into multiple dimensions. Like, you know, the example I showed where we went into 5 or 10 dimensions, where we're using, in that case, it was the points in along a seismic wiggle, but you could also use multiple attributes as well.
Yeah. And actually that could work if you create more attributes than only the semblance for the auto picking.
Right. One of the interesting things on this, Brian, that will be we haven't explored, it will be to use picks for anisotropy, right?
Mm.
So I was thinking, for example, if you think of the semblance as, you know, I think of that a bit like a radon transform. You have an arbitrary complex equation. So if you are doing a 3D or an isotropic shot, then you can think of, you will have perpendicular to the semblance axis where you have the velocities, you will have, basically you will have velocities along the 2 directions, right?
Sure, that's a great idea.
Or you can have a symmetric velocity and then variations along that will be the anisotropy. So that's what I'm expecting to see interesting results with this.
Well, they appear to do that in their paper, but their paper is maybe they just didn't want to give away any intellectual property, but they talk about multiple attributes, but they don't say which attributes they use. They talk about clustering, but they don't, you know, they're very careful not to say what types of clustering. So
yeah, there is a paper, I don't know, I think it was after this, I was just looking DB scan versus k-means, and they compare, you know, they say k-means is not very good compared to DB scan. So in a few quick tests, the Gaussian mean mixture seems to be quite nice.
okay.
I don't know if we have time, Marcelo, it's 5 minutes after, but if you let me share for a second, I can show one plot.
Let me just say something. I have 2 things to say about the clustering methods. Which one do you want to select? And which one works better? Depends on your data set that you have initially. So there is this plot here that you have in the Scikit-Learn website that show that when you have different separations of the data. So which one of those clustering algorithms is going to work? For example, when you have this type of separation, we have a cluster that's outside and another inside here. The k-means is not going to do very well because it's a centroid method and you have a linear separation. But spectral clustering, you can work with non-linear clusters. Also, the DB scan is going to work very well. This agglomerative works well that we showed last lab. The Gaussian mixtures didn't work properly for this one as well, because it couldn't separate 2 distributions in this data set, like one distribution in the middle and another on the outside. And even here, but it works very well on different types of data set. So the way that you choose your clustering model that you want to work with, you kind of need to know a priori how your data behaves. And another thing that I just
Can I just say one thing about that picture, that top one? There's a really nice example in the Goodfellow book where they show the those circles can be separated really easily if you just transform the coordinates to polar coordinates. Then
Yeah.
they become linearly separable.
Oh yeah, I also did a report for the cruise in 2018 for the faces classification, that I saw that there could observe these circular behaviors between the classes, and I did the polar coordinates, and
Okay.
the metric is improved.
And that does the trick, doesn't it? Yeah.
Yeah.
That's great.
And the last thing that I want to show, after you run your Python, if you want this to be converted to a Python notebook, here in the VS Code, you just do right click in your code, and you can export current Python file as Jupyter Notebook and Python file and output as Jupyter Notebook. You can export with the output. That means that's gonna run all the code, or just this one that's just gonna create all the cells. So let's do this one. You just save with the name that you want and where we are gonna export. And now it showed here. And when you open, now you have your notebook back if you want to work, if you prefer to work in a notebook as well. So everything's gonna be loaded. When you plot, the plot is gonna be right below. So just running a little fast here. So it's gonna work as it worked before. Okay, so now I'm gonna stop sharing, and Daniel wants to share.
Oops. That was a very nice lab. Thanks for sharing that. It was good, good overview of all the different clustering methods.
Oh, thank you for joining. And
Thanks.
the next one, we're gonna have Ninoska explaining all the other ones.
Right.
Daniel, you're muted. I don't know if you're speaking. Okay.
Yeah, now I go. Yeah, so this is the semblance. I guess, you know, we'll have to wait for Ninoska to go into all these details. These are some quick tests, but basically we have some script to generate a bunch of models, because the idea we were going to do this supervised first. So we generate with seismic Unix different velocity models and generate many shots and then form CDPs, right? That I think, let me move quickly here up. So these are the CDPs, these are the semblance from seismic Unix. And then here you have a quick example. So the problem that we will face when we do this semblance is you have to select a velocity trend to do that. Right? And in this case, I don't have multiples, but eventually we will have to deal with the idea of generating different velocity trends. But the this is a result with the k-means, and these are the different areas that separate, right? So it didn't work too well. And this is a result with the Gaussian mixtures that selected very nicely all the peaks. So yeah, we can see that when Ninoska present, but certainly, and this is just the first try with Gaussian mixture. It works, you know, just with the default parameters, not even trying.
It looks nice.
Yeah.
Okay, so that's what we had to present for today. If you have any questions, now you can unmute or you can send to the chat, and you're here to reply.
Hey, the good news, I'm sitting out in my backyard right now. It's so nice.
Yeah, today I could walk my dog just wearing t-shirt.
Great.
So one more thing that this could be interesting is to separate primary from multiples, to combine this with the SVM, support vector machines, to separate the zones, right? So then you define the two velocity trends, and then it's a combination of things that we have been thinking, but you can combine in principle either DBSCAN or support vector machines to separate primaries from multiples. And then do the picking. So I think there is a lot of different things to do. The work is just to put together something that you can test all these methods and it's realistic. So this was part of a project that we did in the course last year for machine learning. And so the idea is we could, if we generate a lot of velocity models and a lot of semblances, we can actually compare with neural networks and do a supervised training. So yeah, a bunch of ideas. It's a nice problem to try these things.
All right. Yeah, sorry, I missed it last week because I forgot to, or 2 weeks ago, forgot to post it in my calendar. I just forgot all about it.
Are you in Calgary or are you in BC?
Oh, I'm in Calgary. Yeah. Yeah, don't worry.
You still have your place in BC, don't you?
No, we sold that. We have a place in Victoria now, but.
So you went for somewhere warmer.
Yeah.
Well, I will see you all tomorrow at 10, I guess, during cruise.
Okay.
Oh, that's right. 10 o'clock.
I don't have any more questions, so I'm going to stop the recording.
Yep.
And you can keep talking.
By the way, in case you're looking for books, I was cheating a little bit while you were talking. You know, I can't remember all these methods, and there's a fantastic book by two Greeks, Theodorides and Koutroumbas. Has anybody heard of that? It's called Pattern Recognition. Real fat book, but every one of these methods is in there, nicely described.
Okay, and if you also want,
and actually, it's online. The actual digital copy's online for free if you want to look at it.
Okay.
So I'm gonna look into that definitely.
Yeah, I'll send you the names. They're so complicated, but in fact, I think I have a download of the digital copy. I can send you that.
Oh, nice.
It would be appreciated. I've asked Daniel so he's given me a list of books before I start the PhD. So yeah. My summer is already overly full.
Well, this one is, how many pages? This is the latest edition. It's a 960 pages.
Yeah. I do prefer the book ones because then you can sit with a highlighter and pen and then tag which pages you need to go back to. Because,
well, I was going to ask you, there was a couple of interesting things when they're talking about DB scan. They said there's some tricks people have put in, like putting the graph Laplacian in and things like that. And I'm not sure if they have that in. They probably do in the Scikit-Learn directory, but.
Like I took the stuff from your lab and I used it on a data set that Marcelo and I was using for petrophysics, but the trouble is it's unbalanced. So and of course, everything was trying to come up with balanced clusters.
Couldn't you scale it before, or?
Well, that was one of the questions. The trouble with geology is most of it's shale. And what you want to find is the anomalous events.
Yeah, you had more points in the shales.
Yeah.
Okay.
Well, it was basically contaminating the sandstone with shale fraction.
Okay, so I think those were the same Scikit-Learn options that Marcelo was showing today, right?
Yeah.
Gaussian mixture and k-means. Yeah.
So there's lots of things to work on over the next couple of years. Anyways, see you guys tomorrow.
Good stuff. Nice presentation, Marcelo. Thanks.